Hello, this is Karen O'Brien with FLO-2D Software, and today I'm going to be doing a video on setting up hydrology data for FLO-2D. So we're going to start with the lesson with the regular QGIS project that we typically use, and we'll be using the workshop lesson guide to start this. Video number 1, the QGIS FLO-2D plugin Getting Started, is already available on YouTube. Lesson 1, Part 2, project and data safeguarding. So this is how to open and load projects and how to save them and how to zip them so that you can get them back in case you mess them up in some way. That is also available on YouTube. And the lesson 1, hydrology, rainfall, and infiltration is one we'll be doing right now. So we'll start by adding an inflow hydrograph to the grid, and then we'll assign rainfall and then infiltration. So let's start with this inflow hydrograph. So let me grab the online imagery really quickly. So what you have with this little project is it's surrounded by a large area that would actually feed this project water. Now we're going to just focus on water coming in from this specific watershed and from the southern watershed. Now in this setup, we have an inflow hydrograph that would represent the water that comes from this side of Cave Creek Road right here. So it basically is going to pick up almost everything from this area and send it to this hydrograph. It picks up all the rainfall. Now, typically you might get this from something like a HEC1 or HEC HMS model, but I'm going to be pulling my data from a bigger FLO-2D project. In this area, I think hydraulically speaking, we have some isolation because everything north of this roadway will be collected and will either be running toward an interior outfall from the storm drain system, or it will be running toward the offside of the model. So in this model, we would probably want to account for water from maybe this area right here, maybe water from in here, and this area, possibly these offsite areas, and then will be in inflows like at this point along Bell Road, and then anything that would be feeding the Greenway channel from this area. And then everything else on this side of the freeway starts going this way and leaving the system in the opposite direction. But for today, we'll just focus on 2 inflow hydrographs, one here and one at this point. So I'll zoom in on this area, and we'll see right here that we have a big box culvert that collects all the water from that Cave Creek and adds it to this Grover detention basin. So to get that water into our model, we can use a boundary condition editor and add an inflow node. So I just click this button right here and then select anywhere in this area so that the water will enter this grid and then flow down into the system. It's an inflow hydrograph. These are the other options, but we want inflow right now. And then you click save, and that will open up the dialog so that you can edit it. This very simply just Grover in lets me know that that's the inlet for Grover Basin. It is a floodplain node. We have an inflow hydrograph and the time series. In this case, I have a time series for the 100-year. Well, let's just call this Grover 100-year 24-hour event. And I don't think I need spaces. I don't think it matters, but I just take them out. And then we can get this hydrograph data and add it to the table from external file. At this point, there's no way to import this data. I think this was supposed to connect to a CVS file, but I don't think it's set up. So we'll just get it in the regular way by pulling it out of the project file. So here's the project file, hydrology and the Grover Basin inflow. Oh, this is going to mess up because my my license is bad for that. So let me do this with Notepad++. And I wanted you to see something about this data, is that these are tabs. And the reason these are tabs is because we are going to paste this into the table. Now, don't be confused. All FLO-2D data usually requires spaces. All the FLO-2D .dat files are all space delimited. But in this case, I'm going to hit Control-A to select everything. I want you to note one thing. When I select all, when I select everything, it has to select this entire line, line 241. So if I turn on the reveal codes, I want to see that it selected that carriage return code. So I'm going to copy that. Control-C will copy that, and then come back to QGIS and put my cursor in cell number 1, row number 1, cell number 1, and click paste. And that will put that data into the editor. And then if you look at the plot, you can see a plot of your data. This is CFS versus time. And that is your inflow hydrograph for this point. Now I don't have to hit save again, but I do need to schematize it so I can convert it from user data into FLO-2D data. So if I schematize it, you can see that it sets that up as a FLO-2D specific. It identifies that this is the actual cell it's assigned to. And I'll just turn that off for now. And we can go on to the next inflow node. So, and I just want you to know that you can have as many inflow nodes as you need on a project. You don't have any limitations on that. The limitations are that you try to set them up in a location that would be like a point of concentration. In this one, I'm going to set it up right here because I don't have the channel in right now, but I can still put the inflow hydrograph in. So I'm going to set another one up here. Again, click the edit button or add a point. I'll just click it right here and click OK, and then I'll save it. And then back to the same thing. So this one, instead of, we'll identify it as the greenway in. And we also need to add a time series. So I use this button right here to add a time series, and we'll call that time series Greenway in 100 year 24 hour. Click OK, and it's the same thing except this one is located in lesson 2. And I don't actually bring this one in until lesson 2, but for the purpose of the video, I just wanted to show you how to do this. So hang on, let me find lesson 2 data. And in lesson 2, we have our greenway inflow here. So same thing. Oh goodness, I apologize for that. I'm gonna have to get that reactivated. Control-A to copy, or Control-A to select, Control-C to copy. Put it into the first cell and paste. And now that one is also set up. So again, we schematize it. And you don't have to schematize every time. You can schematize at the end. That's fine too. All right, so that's your inflow hydrograph. Now, the next thing will be to set up the rainfall. So I'm just going to zoom back out to the full map and go over to the rainfall editor. Okay, so this one's very simple. You just click select simulate rainfall. For this storm, we use a value of 3.74. And I don't have a rainfall abstraction, so I'll leave that as 0. I don't have buildings right now, but if there were buildings, you'd want to just click this switch to turn the rain on building on. It's okay to click it even if you don't have buildings, it'll just ignore it. And then we need to add the rainfall distribution curve. That's this guy right here. Now we also have this rainfall distribution curve back in our data in our hydrology folder for lesson 1. Here is our rainfall distribution curve, and we also have all of the rainfall distribution curves that were available in GDS. You can get any of these curves, or you can make your own because these are very simple. I'll open one up just to show you how simple these are. Let me go back to our original one. Oh, I did it again. I'm just going to do this all day, so just get used to it. Okay, so here we have the rainfall distribution curve. You can see how simple it is. It starts 0 time and 0% rainfall and goes up to 24 hours and 100% rainfall. So this is 0 to 1 represents the percent of accumulated rainfall. So most FLO-2D data is like a decimal percentage. It's 0 to 1, not 0 to 100. Just keep that in mind. That's important. Now this one's a little bit different because we have a selection tool that will select the data. So all I have to do is open this, and I can go and grab that selection tool and grab that file, and it will load the data and import it into the model, or import it into the map. And then if you plot it, you can see this is your distribution curve for this specific storm. Now, if you need to do other storms, what you'll want is probably a different data set, FLO-2D data files for every storm that you want to do. Alrighty, and we also have the ability to do some spatial variation. Now, this is a uniform rainfall distribution right now. So if we were to run the model right now, every single cell would get exactly 3.74 inches based on this time distribution. But if we want to use spatial variation based on a depth area reduction, we can also add that. So if I bring my spatial distribution map from the NOAA Atlas 14 onto my map space, and all of this stuff is available in the hydrology folder. Let me get this out of the way so that it's at the bottom, and then I'm going to zoom out to this so that you can see what it is. So this is the NOAA Atlas data for the whole state. But obviously we don't care about the whole state. We really just are interested in our project area. So let me show you how this works. I'm going to go back to our project area, and I'm going to check the spatial variation, and then I'm going to click this button, and it's going to use our NOAA Atlas 14 data to set up the depth area reduction factors for our project. So it's going to take this raster and it's going to warp it to our grid, and then it's going to sample from the center of the cell each one of the warped rasters. So let me show you how this works. We'll click OK. It's going to perform the procedure, and then once it tells us it's done, okay, so what it says is that the data was stored in this layer and that all the cells were sampled. And I'm going to click OK. And if you keep this turned on, when it exports the data, it will export that rain ARF data. So this is what it did. Hold on, let me jump down here and grab another layer, and then I'm going to pull another raster onto here, onto our map. So this is the interpolated raster that was calculated. So I'm going to drag this onto our map space so that you can see the warped and redefined map. So this is the Atlas, NOAA Atlas data for our grid space. Has this max and min values. So what it's going to do is it's going to calculate a depth area reduction factor for our project based off of these values. So it's going to take the 3.752 as the max, and then whatever value of the cell over that 3.752 becomes the rain ARF, or the depth area reduction factor for that cell. Okay, so let me show you how that works. I'm going to go ahead and turn these two off, and then let's check the control parameters to make sure the rainfall switch is on, and export the project into Lesson 2 export folder. Well, I'm actually supposed to be in Lesson 1, but again, I'm setting this up in Lesson 2 so that I can be ready to do Lesson 2 when I'm ready to go. All right, so sorry, I didn't mean to confuse you. So let me go back here and let's take a look at that data that we just created. Let's see, there's a lot of data in here. Let's just do this. Let's do that again. Okay, so we have the control data, the tolerance data, the topo, inflow, and rain. All right, let's see what we just made. Now, these are the files we just exported. I'm going to open 2 of these in Notepad++. All right, and I think we can also take off that extra symbology just to clean the data up a little. All right, so let's go to the rain file. Now you can see here that we have the control data for our rainfall, 3.74 inches. If you're doing metric, that'll be millimeters. And 1 means that we want the rain ARF. Now here is the distribution curve for the rainfall. It goes from 0 time to 24 hours and 100% of that. And we also get a rain ARF factor. So this is very simple. This is just a, again, this is a decimal percentage. So this means that 99.9% of the rainfall will fall on this cell. 99.9% of this 3.74 inches will fall on this cell. And as you go throughout the project, you'll see that that number varies based on the data that came off of that NOAA Atlas raster, that original NOAA Atlas raster that was warped and aligned to our system. So the good news is that you do not need to have this data is in inches. This data can be in whatever you want. All you need to be able to do is to calculate the ratio. Now, the reason I say that is because Flood Control District of Maricopa County has this data already set up in inches for all of their projects and for all of their rainfall design storms. But when you go onto NOAA and you get this data for yourself, it's going to be in something like inches per 2,000. It's going to be something like inches over the resolution of the raster. And the resolution of this raster was 2,000 by 2,000 feet. Okay, next. That takes care of rainfall data and spatially variable rainfall data based on a depth area reduction. Now, let's move on and get right into infiltration. So, for infiltration, we have, back here in lesson 1, we have 2 shape files. And we have 3 sources of infiltration data, but I'm going to focus on 2 of them. So, let me grab this land use and soils shape file. There's your land use. And there's your soils. And then we'll take a quick look at the data that's required for these two shape files and for setting up infiltration. So if we look at the infiltration editor, we can set up our global infiltration variables. Now I'm going to start with the global SCS because it's fairly commonly used. So here's your global SCS, and I like to just add a kind of a generic curve number in here that would represent any cell that didn't have coverage from the shapefile, but our shapefiles have complete coverage, but I still need some placeholder data in here, so that's a fine way to set that up. Click OK, and then that will allow you to calculate your curve number data from one of your shapefiles. So in this case, I believe our curve number is in the soil shapefile. Yeah, curve number is right here. So we can use this shapefile to define a curve number. So I'm going to click Calculate the curve number, and I'm going to use the S key to get me down to the soil layer and change the fields to curve number and click OK. Now that is takes a bit of time, so I'm going to pause the video while that's calculating, and then I'll come back when it's complete. Okay, when that curve number is complete, is finished calculating, you're going to get the message that it's done. If it failed, it'll give you a fail message. And usually if it fails, it means something's wrong with the shapefile, like maybe there's some overlapping or something. And you can typically fix it by fixing geometries or simplifying your shapefiles or something like that. Okay, so now let's take a quick look at what we just did. We calculated the infiltration data for the SCS areas. So if you look at this now, you can see that we have a curve number for every cell. All right, I'm going to move right on because this is getting a time-consuming process, so I'm going to go straight into setting up because you should probably get and understand curve number data and how to set up these systems for it. It's usually pretty widely available. And one more thing that's important: when FLO-2D does the when FLO-2D starts, the curve number data will take the rainfall right off the grid before the simulation starts. So infiltration from the curve number comes right out of the rainfall. Infiltration for the green amped comes out of the, it's based on the routing. So the water hits the grid and then it starts to infiltrate. All right, so I'm going to put in some junk placeholder data here. Let's see. Let's just because I need to write this data to the data file. Now, the global values for the infiltration will be added to this for the next release, but for now you have to add them in yourself. So we're just going to put, this is just bogus data. Click OK because I have complete coverage. And then I'll click Calculate Green Amped. Okay, so here's my soil layer. And this one was already set up, but if it's not, you have to come and pick these yourself. So soil layer, and it looks like they're kind of wrong anyway. So this one is XKSAT. Rock outcrop is fine. This is the effective impervious, and this is the soil depth. Land use, this would be the initial saturation. For this one, I'm not going to calculate from the vegetative cover. I'll just leave that one blank. This is the initial abstraction, and this is the impervious, percent impervious. Now, this impervious comes from things like streets and buildings and pavement and such. Then I click OK, and we'll let that calculate. And again, I'll pause the recording and come back when it's complete. Okay, the green amp parameters are finished, so now I want to take some time to look at this hydrology manual so that you can kind of get an idea of how to create this data. So this hydrology manual is coming from the Flood Control District of Maricopa County. You can get it right off their website. This is how it works. Okay, so I'm going to highlight this guy right here, and let's see, right-click and open the attributes table. Now this is pretty simple. This is just a soil map that comes straight from the NRC, and then you can, so it will probably contain the XKSAT and the rock outcrop and the effective impervious areas, and then you would probably need to add the soil depth to the map. From the table 1, this is what will be calculated from these values. Okay, so you'll get an average XKSAT over the grid, and this will be calculated as an average as well, and then the d theta will also be calculated. So all you have to do is to find these parameters right here. And again, this one's usually comes from the soil cell. This one might come from the soil cell, and this one might come from it too. This one you have to develop based on your how your land, or how, I would say this one's kind of a limiting factor to limit the total volume of the infiltrated material on each cell, and so this will only infiltrate, in this case, up to 0.333 feet. Now let's go back here and let's bring up the land use. So let me bring this one down a level. Now this is the land use data. You can see it's a lot more complicated. It has buildings, it has streets, it has parking lots, it has parks, all kinds of areas that add additional information to this. Now the way that these are defined, they're not so difficult. You can take your typical land use map that you might get from the USGS, and you can add a street layer to it, and you can add a building layer to it, which are usually available from your county. You might be able to add that park data to it from your county as well. But things like parking lots, you might find that you have to add yourself. And then once you get that data in there, this is what you'll do. You'll open the attribute table here. And what you see is that you need the initial abstraction, you need the percent impervious, the vegetative condition if you're going to use it, and the initial saturation condition. Now what I have from Maricopa County is another table that outlines how they define these parameters. So you can see here in this second table, table 4.2, that they have, based on the type of land use that they have, if it's residential, if it's industrial, commercial, do they have pavements and rooftops, they have each of these fields are identified and the value, and they tell you the value you might want to use. Now, a lot of these, for example, if you have lawn or undeveloped range land, you might have to define this yourself. But they're not so difficult. You pick a value of what you need and you assign it to each of these individual polygons. And you'll see what I mean here. We have, as highlight this and I select these, you can see that these individual polygons kind of represent similar land use classifications. Alrighty, so that's how you set up your green amp data. And let me zoom back out to that layer and turn them off because the calculation was performed, and now we have data in both the green amp and SCS. So typically when you do your project, you're only going to use one or the other. You can use both, and if you use both, you just have to set up a code that identifies that you want to use both of them. So let's make sure that our infiltration button is checked and then export the project again so that we can see how that is set up. All right, now you can see here that we exported the rain.dat and the infill.dat. Alrighty, and let me go back to the place where I exported the data and open the new data. Alright, so we have the rain, inflow, and we want infiltration. Alright, so you see here that this is placeholder data. It's pretty much bogus. We are using, it's set to 1, so that means we're using green amped. And if it was set to 2, it would be SCS. And if it was set to 3, it would be both. But we only want green amped. Now you'll also see, because I did my SCS first, that I also have SCS data in here. I don't actually want it or need it, but I don't think it'll hurt anything. I think it'll just ignore it. But I'm just going to get rid of it anyway, just in case. Now, again, I don't really think it's necessary to get rid of it, but I'm just going to do it anyway because I want to run the model now. Okay, also wanted to show you the inflow.dat. So here's your inflow.dat file. You see this is a floodplain node. That's the grid element number. And this is the hydrograph data. So you can see that this is space delimited, not tab delimited. And it goes from 0 to 24 hours. And this is your hydrograph for that cell. And then you see that you have 2 of them. So we have one for the Grover Basin and one for the Greenway channel. Okay, that is it for creating the data. Now I want to just run the model and just leave it running. So I'm going to pause the video while I run the model. Okay, so the model was run and now it is completed, and I have mapped some of the data and brought it back into the project. So a couple of things. So now the final set of this discussion is to define the boundary condition, and that's why I tried to run the model first so you can see where the water wants to go. The water wants to pond down on this side of the project. So this is the area where the boundary condition is required. So for now, I have no channels and no storm drains. So for now, all the boundary condition will just be the floodplain. As you enter the other features, like the channels, storm drains that might take water off the project right here, channels that take the water off the project right here, and then storm drains that might have like take the water off the project right here, you can set up a downstream boundary condition to handle all of that. Alright, so a boundary condition editor is set up with a polyline, and for now we can just assign it to the edge of the boundary. So I just click there, and then down here at the side is click there, and then right click, outflow node, OK, and that becomes a boundary condition. Over here you click save and change over to the outflow tab, set that from a floodplain outflow node with no hydrograph, and click schematize. And as you can see right in here, the outflow conditions are assigned. And if you go to the export and export the project again, now we have the exact same condition as we had before, except now the outflow node will be defined as well. And so now you can run it again. So the idea behind running the model interim, don't just build the whole project, build it in stages, and at the end of every stage, go ahead and run it. So you're doing two things. First of all, you're defining you're finding conditions that need to be set, and secondly, you are checking for problems with the data. So you can see here that we clearly need a channel. You can see here that we clearly need a hydraulic structure to prevent any overtopping of the water on this street. And you can also take a look at some of the export files for review, which we'll do in another video. So the next video will be how to start to review these models. So I'm going to stop the video now, because that's basically the end of how to set up the hydrology for a FLO-2D simulation.